Sarah, you've highlighted cross-validation as a superior method for model evaluation. Can you break down why it's better than a simple train/test split?
Yeah, a simple split can be misleading. You might get lucky and have all the hard cases in your training set. Your test set would look great, but that's not a real-world scenario.
So, cross-validation avoids this luck factor?
Exactly. Each data point gets its turn to be the test set. It gives a much more realistic picture of how well your model will generalize.
But isn't cross-validation computationally more expensive?
It is your training K-models. But the gain in robustness and accuracy, especially with complex datasets, is worth it.
Okay, so tell me more about stratified K-fold cross-validation. It's new to me.
It's crucial if your data has class imbalances. You want to ensure that the percentage of each class is similar in every fold. This prevents one class from dominating your results.
Wow, I see. What about choosing K?
There are guidelines. Generally, 5 or 10 is a good starting point, but sometimes you might want more folds for bigger datasets. It depends on your computational resources and the nature of your data.
How about a real-world example?
Imagine medical diagnosis models. If you're training a model to detect rare diseases, a simple split might miss cases. Cross-validation, especially stratified K-fold, would give more realistic predictions for the general population.
So, you're saying it's important to be realistic about how a model performs on real-world unseen data?
Exactly. Cross-validation helps us get a clearer picture.
Great explanation. Thanks, Sarah.
You're welcome, Jane.
So, the takeaway is that cross-validation, despite its added cost, provides more reliable model performance estimations.
Yep, and for specific use cases like imbalanced datasets, stratified K-fold is a necessity.
Got it. This is really helpful. Thanks. Sarah, you mentioned stratified K-fold cross-validation. Why is it so important for skewed datasets?
Well, if your classes aren't evenly distributed, a standard K-fold can give you a misleading accuracy. Imagine a rare disease detector. Using a standard split, you might only test the rare disease in the test set.
So, you'd accidentally overestimate the model's performance on a rare class?
Exactly. Stratified cross-validation, ensures that proportions are similar in each fold. That prevents overrepresentation or underrepresentation of any class.
Okay, but we talked about other types like leave one out. Are they superior?
It depends on the data. Leave one out is intense computation-wise but can provide great estimates with smaller datasets.
Interesting. Are there practical implications for using different approaches?
Medical diagnostics, for example, could benefit significantly from stratified K-fold or leave one out, especially if rare diseases are involved.
So, N_splits and CV parameters are involved. Could you give a quick example?
Shuffle split lets you pick parts of the data for training/testing in many iterations. That's useful if you need a general evaluation.
How about choosing K? Any guidelines?
Generally, 5 or 10 is a good starting point, but it depends on dataset size. Larger datasets might need more folds for more stable results.
So it's a trade-off between accuracy and processing time?
Precisely. Different techniques have various computation costs. You need to consider your computational resources and data size,
What about the IRIS dataset example? How did it expose flaws in standard K-fold?
The IRIS dataset has classes ordered. A standard K-fold could yield zero accuracy in this specific case.
Wow, that's quite a problem.
Stratified K-fold addresses that issue. It keeps class distribution consistent.
So, to recap, stratified K-fold is crucial for classification. Leave one out can be superb with small datasets. But shuffle split and others offer different advantages.
Absolutely. The best choice depends on your specific data needs.
So, it's crucial to consider data characteristics for optimal evaluation.
Exactly. And we can use parameters like shuffle to make different splits within the same strategy.
Great. Thanks, Sarah. This has been incredibly insightful.
You're very welcome.
Sarah, you just introduced Group K-fold. So it's like stratified, but...
Right, it's for when data has groups. Like if you're studying patients, you wouldn't want a patient's data in both the training and test sets.
Got it. So each group is either all in training or all in testing. Makes sense.
Exactly. Group K-fold prevents that leakage.
Great example. So, what's the big deal about grid search?
We want the best model, right? Grid search tries every combination of parameters.
Wow, that's a lot of testing.
Precisely, so it might use up computing resources, but it is very comprehensive.
Okay, why split into training, validation, and testing?
Well, you don't want to tune your model to your test data. The validation set is like your second opinion.
So, we're overfitting to the validation set then?
If you keep changing the model to get the best score in the validation set, you'll get better validation scores but worse real-world generalization.
So, the test set is like your final verdict.
Exactly. It's the unbiased evaluation.
What if our training set is really small?
Then the validation set needs to be smaller too. You need to be thoughtful on how to split your data.
So, the proportion matters?
Yep. There's an art to finding the right split for your data. Usually 70/20/10 for train/validation/test is a good starting point, but it depends on dataset size.
How to choose the parameters for the grid search?
It's a systematic testing. You'd need a range for the parameters. Often people start with a wide range to discover which parameters are most influential.
If you overshoot in the grid search, does it just try the same values?
The whole idea is to search in a range, you know? You often start with a guess, see what the best performance is, then you refine it in subsequent steps.
What if grid search CV is much slower than a naive loop for a huge dataset?
If it's taking too long, you might want to tune a narrower range of parameters, use a different method like randomized search, or just a subset of the data in early iterations for tuning.
So, trade-offs all the way, huh?
Always. Computational cost versus the potential gains in model performance.
So, the test set is the ultimate truth for evaluating the trained model.
Correct. It measures how well your final model does on truly unseen data.
What is the best split for a model?
It's hard to say. It's data dependent. 70/20/10 is a common starting point but not always ideal.
So what should a data scientist keep in mind when choosing the split percentage?
Think about the size of your data and the importance of getting a good validation set to avoid overfitting.
Thanks, Sarah. This is illuminating.
You're welcome.
Sarah, the last method, tuning with just a train/validation split, felt a bit fragile.
Yeah, Jane, it's true. The results could change a lot depending on how we slice up the data, right?
So, cross-validation fixes that, right?
Exactly. We're now looking at many possible train/validation splits. It's like having multiple opinions on the best parameters.
Makes sense. How does grid search CV do that?
It automatically tries every combination of parameters in your grid, doing that cross-validation for each combination.
Whoa, so a lot more computation.
Absolutely, but it's worth it. We're getting a much more reliable estimate of how well the model will generalize. Imagine tuning a car engine. Testing only one setting for each adjustment is risky.
You're saying we need the best, most precise setting?
Precisely. This way we find the parameters that work best across different subsets.
So, is grid search CV just using cross_val_score under the hood?
Essentially, yeah. It makes the process much smoother and less error-prone.
So, does it just pick the best mean validation score?
Yes, but it also trains a new model using the entire training set with the best parameters.
So, why is it important to still have a separate test set?
We want a truly unbiased final evaluation. We don't want the test set influencing our parameter choices at all.
So, how many models are being trained if we have a big grid search?
It depends on your parameter grid size and the fold count in cross-validation. A lot more than a single train/validation split, but a reliable result.
What about a smaller dataset? Would grid search CV be better than a single split?
Absolutely. With smaller datasets, the variability from one split to another is even higher, making the more robust method, grid search CV, more worthwhile.
Is it always a good idea to use a 5-fold cross-validation?
It's a common choice and often a good starting point. It depends on how computationally costly it is to do more folds. 10-fold is another common option.
So, are there alternative parameter tuning methods?
Yes, there's randomized search. It's less thorough but can save time if the grid is massive.
Sarah, what's a practical use case for Grid Search CV?
Imagine training a model to predict customer churn. We could use Grid Search CV to find the perfect balance of parameters for our model, ensuring it accurately identifies customers likely to churn.
Sarah, what are the best visualizations to understand cross-validation results?
Plots showing how different parameter values affect the mean cross-validation accuracy are useful.
Thanks for clarifying that. It's really helpful.
You're welcome, Jane. Glad to help.
Sarah, these heat maps are fascinating. It's like looking at a landscape of model performance.
Exactly, Jane. You can see the peaks and valleys of accuracy, visually representing how sensitive our model is to the choices we make.
So, what do these different colors mean?
Lighter colors mean better cross-validation accuracy, darker colors lower accuracy.
Wow, that one heat map shows huge variations in accuracy.
Yep, it's really highlighting which parameter combinations are best, and often pinpointing areas of the parameter space you might want to revisit.
So, how do we read a stripe?
A stripe means one parameter is really significant in the results. The other parameter might not be important.
Makes sense. How do we decide how wide the parameters should be?
Well, you start broad, then narrow your focus based on these visualizations. You see where accuracy varies greatly and change ranges there.
So, do you always use a heat map? Like, are there better ways?
Heat maps work well for 2D plots, but for 3D or more parameters, you'd use a different way, like 3D plots or interactive visualizations.
Okay, so is there a way to find a smaller grid?
Yes, these visualizations help you to choose your next steps. The bottom left of one heat map shows constant values. That suggests a search in that region wouldn't be very fruitful.
It looks like we can simplify our search.
Exactly. You're focusing your effort where it matters most.
But if the search range is too small?
Then you get a very incomplete picture. You might miss some potential optimal solutions.
So, what's the key takeaway?
You're not just blindly testing. You're analyzing the results to intelligently refine your search process.
That's insightful. This is much better than before.
Absolutely. Instead of randomness, you're now making educated guesses using insights.
How about dealing with the kernel parameter?
You can use a list of dictionaries for perm_grid. One for each kernel.
Clever.
That makes it flexible and avoids unnecessary calculations for unrelated parameters.
And if you don't see any changes in performance?
That can tell you whether that parameter is really needed. It might not affect the model.
So, what about the real-world example?
Think of designing a new car. First you test over different engine sizes, then you narrow down to specific parameters like RPM ranges. Iteration is key.
That analogy is helpful. Thanks, Sarah.
You're very welcome, Jane.
Sarah, you were talking about how to really evaluate model stability.
Yeah, nested cross-validation is a powerful tool there.
So, it's like using cross-validation inside cross-validation?
Exactly. You get a much more robust estimate of how well your model generalizes.
But is it always necessary?
No, Jane. For smaller datasets or models where speed isn't a huge issue, a good training/test split and regular cross-validation are totally fine. But nested is critical for big data and really complex models.
So, what's the trade-off?
Computational cost. Nested cross-validation takes longer because you run cross-validation multiple times.
Right, and you mentioned parallelization?
Yeah, you can spread those calculations over many CPU cores or machines. It's like multiplying your computer's power.
How do we decide when parallelization is worth it?
It depends on your computer resources, the complexity of the model, and the size of your data. You want to look for situations where computation time significantly impacts the quality of your work.
Now, evaluation metrics.
We need to consider the real-world application. Accuracy or R-squared might not be the best metric.
How about that self-driving car example?
Right. You might need a different metric, pedestrian collision rate, or distance from pedestrians. The business impact is fundamental.
So, we need to think about the why of our model.
Exactly. You're not just optimizing an algorithm. You're solving a problem. The metric must directly reflect that goal.
Makes sense. Can you give an example in a business setting?
Sure, a website wants more user engagement. Instead of clicks, they might measure time spent on site. That's a business metric.
So, what's the takeaway?
Choosing the right cross-validation method and evaluation metrics is critical for reliable and impactful models.
And we have to factor in the cost of computation.
Absolutely. Balancing stability, speed, and real-world impact is key.
Thanks, Sarah. This is really helpful. Sarah, you were saying that simple accuracy isn't always the best measure.
Exactly, Jane. It can be very misleading, especially when your data is imbalanced.
Can you give an example?
Imagine predicting if someone will click on an ad. Most ads don't get clicked. So, a model that always predicts no click could be 99% accurate, but it's useless.
So, what should we look at instead?
We need to think about the real consequences of errors. A false positive, someone seeing an ad they don't want, is different from a false negative, missing an ad someone would click on.
How do we quantify that?
We try to find a surrogate metric. Something easier to calculate that reflects the actual business goal.
Like what?
For example, in cancer detection, a false negative is far worse than a false positive.
So, how do we figure out the best surrogate metric?
Well, we need to define the business goal. Is it minimizing costs? Is it maximizing conversions?
Interesting. Is there a way to visualize these different error types?
Yes, confusion matrices are great for this. They show the counts of true positives, true negatives, false positives, and false negatives.
So, a confusion matrix helps us see which errors have the biggest impact.
Absolutely. It shows us the relative magnitude of different types of errors.
So, if a model is just predicting the majority class, it's still 90% accurate. But does that matter?
That's the problem. High accuracy doesn't always mean a good model. If all our model does is predict the most common outcome, it's really not learning anything.
What other issues do we need to think about?
Imbalanced datasets are a big one. One class vastly outnumbers the other, which, as I said, dramatically skews accuracy.
Sarah, so, instead of accuracy, what should we be focusing on?
Focusing on the business metric. We need to consider the trade-offs between false positives and false negatives.
How do we find the right business metric?
You have to understand the business goal. If it's to maximize conversions on a website, time on site might be a better metric than clicks.
So, how do we decide what to optimize for?
It depends completely on the problem we're trying to solve.
Okay, let's explore some more specific examples.
Yes, let's.
Sarah, you were talking about confusion matrices. Can you unpack that a bit?
Sure, Jane. A confusion matrix is like a visual report card for our model. It shows how well it classifies things.
So, how does it work?
It's a grid. The rows show the actual classes, and the columns show the predicted classes. The numbers tell you how many items in a class were predicted correctly or incorrectly.
So, what does this mean for our click prediction?
We look at true positives, correctly predicted clicks, true negatives, correctly predicted non-clicks, false positives, predicted clicks but no click, and false negatives, missed clicks.
So true positives are good and false negatives are bad?
Exactly. But the balance between false positives and false negatives is crucial. In ad click prediction, it's often very different.
How so?
A missed click, false negative, might mean you lost a potential sale. A predicted click, false positive, is just wasted ad space.
So, are we optimizing for minimizing false negatives?
That's often the case, but not always. Sometimes false positives are the bigger problem. For example, in fraud detection, a false positive can shut down legitimate transactions.
So, that's where precision comes in?
Exactly. Precision measures how many of our predicted positives were actually positive.
And recall measures something else?
Recall measures how many of the actual positives we predicted correctly. It's a balance, Jane.
Is there a way to combine these?
The F4. It's the harmonic mean of precision and recall. It gives you a single number representing a balance between the two.
So if we look at the F1 score, we can evaluate the balance better?
Yes. For imbalanced datasets, F1 score is a better reflection of performance than just accuracy, as it accounts for these balances.
So, a high F1 score for a particular model would be more indicative of a good model?
Absolutely. It tells us how good a model is at identifying both true positives and avoiding false negatives.
Can you show an example of how different models compare using F1 score?
Sure. We can see a large difference between models that just predict the majority class and one that actually learns patterns.
So, the confusion matrix and precision/recall are like a much more granular view of our model's performance?
Much more comprehensive. It helps us select the best models, especially in nuanced problems like click prediction and medical diagnosis.
Sarah, you've been talking about these fancy metrics like precision and recall. Can we relate this back to our ad click prediction?
Absolutely, Jane. We can see if our model is good at finding actual clicks, and not just falsely predicting clicks.
Okay, so how do we pick the right threshold?
It depends on your business goals. Are you more worried about missing real clicks, false negatives, or wasting ad space on non-clicks, false positives?
That makes sense. Missed clicks seem like a bigger problem to me.
So you'd prioritize recall.
Right. But how do we actually change the model's behavior?
You don't change the model. You change the way it interprets its results. Think of a threshold.
So if a model gives you a click probability, you just adjust the cutoff?
Exactly. If you need higher recall, you lower the threshold. If you need higher precision, you raise it.
So a lower threshold equals more clicks predicted equals higher recall, right?
Yes. You're more likely to catch more actual clicks but also to get more false positives.
So, what if we're trying to balance both?
Then the F1 score is crucial. It tells you how well the model balances precision and recall.
How does this look in practice?
With classification_report you get precision, recall, and F1 score for different classes so you can really see how it performs on individual clicks.
So, if I lower the threshold, I might get more clicks but also some incorrect predictions?
Precisely. It's a trade-off and you have to pick a balance.
Sounds complicated.
Can be, but the classification_report makes it easier to understand. You can even plot precision recall curves to visualize the trade-offs.
So, a plot could show the relationship between different thresholds and precision/recall directly?
Exactly. It would really show the trade-off visually.
That seems very helpful.
It is. You can then see if a threshold will help us achieve our goal.
If we set a threshold too low, what might happen?
More false positives and possibly more missed opportunities as well.
Interesting. So, it's a careful balance.
Absolutely. And remember, always use a validation set when adjusting thresholds, not the test set.
Why is that important?
Otherwise, you'll get overly optimistic results that don't translate to real-world performance.
Excellent point. So, the trade-off between precision and recall is crucial, and tools like classification reports and precision recall curves can help us find the balance that's optimal for our business.
Exactly. It's all about understanding the nuances of your model's output and its impact on your specific business goals.
Thanks, Sarah. That's very insightful. Sarah, these precision recall curves, they're like a whole new world.
Yeah, Jane, they show you the whole picture, not just one snapshot.
So, how do we read one?
Think of it like a map. Each point shows precision and recall at a certain threshold.
Okay, so a point up high means good precision and recall?
Exactly. The closer the curve gets to the upper right corner, the better the model.
So, curves that stay high for most of the curve are better?
That's right.
How do we know which curve is best overall?
We can use average precision, or look at the area under the curve for a summary.
So, if a curve flattens out, what does that mean?
That means the model has a more balanced precision recall relationship at some point on the graph.
But these curves are really hard to interpret.
It's like a spectrum, Jane. It's about understanding your business goals, and then looking at which thresholds best meet those goals.
Like, in ads, a really precise model that misses a lot of clicks is useless.
Right, and precision recall curves tell us about that trade-off.
How is this curve better than just the F1 score?
The F1 score is just 1 point on the precision recall curve, Jane, while this shows all possible operating points.
So, ROC curves are similar but instead use different measurements?
Precisely. ROC curves plot true positive rate versus false positive rate.
This is amazing. Can you give an example?
Imagine we're targeting a recall of 90% for clicks. We can use the curve to find the threshold to achieve that level.
So if a model performs worse at higher recall, do we use something else?
Absolutely. It all depends on the business goals. Precision recall plots give us a broader view.
Makes sense. What about a situation with extremely imbalanced data?
Precision recall curves can be very helpful in these situations, Jane. We can see how a model performs on the minority class as well as the majority.
So, ROC and precision recall curves offer more detailed insights into trade-offs.
Absolutely, providing a more comprehensive understanding. Always use a validation set when choosing an operating point, though.
I'm getting it. It helps us make sure our model is balancing precision and recall.
Exactly. These plots really illustrate the trade-offs for all thresholds. And they are a really important tool in evaluating models.
It's much easier to understand our limitations.
It is, Jane. We can see exactly where our model shines and where we need improvement.
Sarah, ROC curves, they're visual, but how do we use them?
Okay, Jane. Imagine you're tuning an alarm system. A high AUC means it rarely mistakenly triggers on quiet days.
So, AUC is like a measure of how well it separates the important from the non-important?
Exactly. It shows how often the model ranks positive examples higher than negative ones.
How's that different from accuracy?
Accuracy tells you overall correctness, but AUC considers ranking, essential for imbalanced data.
Like misclassifying a rare event?
Yes, AUC cares about the ordering, not just the classification itself.
So a high AUC is good, even if some samples are misclassified?
Correct. A higher AUC means better ranking of positive samples. That's helpful in scenarios with skewed data.
So, what about this confusion matrix? What does it show?
It's like a spreadsheet of your predictions. Rows are actual labels, columns are predicted.
And higher numbers mean better prediction?
Not necessarily. It helps you see where your model misclassifies.
So you're seeing which predictions are mixed up?
Exactly, Jane. This helps identify weak spots and where improvement is needed.
Makes sense. If one cell is high, it's good?
Yes, but also pay attention to the others.
Okay, so in the digit example, a high AUC means the model is ordering digits correctly, even if it makes mistakes?
Exactly. A high AUC means the model can reliably distinguish the key features, even with an imbalanced digit dataset.
Okay, so how do ROC curves change as we change model parameters like gamma?
It shows us how well the model is separating positive and negative points with different thresholds for gamma.
So, we're seeing a continuum of performance, not a single result?
Exactly. Understanding the range is crucial for practical applications.
So, is AUC better than average precision?
It depends. AUC focuses on the ranking, while average precision cares about the balance of precision and recall.
So, which do you use?
It depends on your problem. For ranking, AUC is great, but average precision is helpful if you need a more balanced perspective.
I'm getting it. Thanks, Sarah.
You're welcome, Jane.
Sarah, you've shown us ROC curves, but how do you pick the best threshold?
Great question, Jane. That's not about the curve, but a separate validation set.
So it's like finding the sweet spot.
Yes, testing on fresh data.
Okay, now, what's this classification report?
It gives precision, recall, and F1 score for each class.
So, like, how well it predicts each digit.
Exactly.
What if one class is super common, like 99% of your data?
Accuracy might be high, but these other metrics can highlight real problems.
Okay, so these F1 scores, what are macro, weighted, and micro?
Macros equally important for each class. Weighted is weighted by class size. Micro is total.
So, micro is more overall?
Yes, overall performance, even if one class is much bigger than the others.
But which is better?
Depends on what you care about.
Like, if your task needs a balanced response?
Then maybe macro is better.
Got it. Now, imagine a loan application. How do you think these metrics are important?
F1 score can help pinpoint risk factors by considering both the precision of your risk model, correctly identifying likely defaulters, and its recall, identifying all potential defaulters.
Why is this crucial?
Imbalanced datasets mean rare events matter.
So, picking the right metric is crucial for loan applications?
Crucial.
Wait, so are you saying that using these evaluation metrics can make a difference in how a loan is evaluated?
Exactly, Jane. It helps find areas of improvement.
Okay, so using ROC, classification reports, and confusion matrices together paints a broader picture.
Precisely. It's more than just one number. It's about understanding the details behind the performance.
And that's vital for practical applications.
Exactly, Jane.
Can you give a real-life example where using the wrong evaluation metric could have huge consequences?
Absolutely. Imagine medical diagnostics. Using accuracy might mask a crucial failure to identify a critical illness.
So, these metrics aren't just for the algorithm, but also for the bigger picture?
Absolutely. You need to interpret them in context, like understanding the stakes of a medical diagnosis.
So, choosing the appropriate metric matters.
It absolutely does.
Thanks, Sarah.
You're welcome, Jane.
Sarah, so we've been dissecting these fancy metrics, but you keep emphasizing the why behind them. Why is this so crucial?
Absolutely, Jane. Accuracy is easy to calculate, but a model that's 99.9% accurate in predicting something that happens 0.1% of the time isn't terribly helpful if it misses those critical cases.
Right. Like a medical diagnosis or fraud detection, where a false positive or false negative could be huge.
Exactly. We need to understand the potential consequences, right? What's the cost of a false negative in identifying fraud versus a false positive?
So, how do we figure that out?
You have to talk to the people who'll be using the model. If it's for loan applications, we need to understand how the bank evaluates risk and the potential financial consequences of misclassifications.
Ooh, so that's a crucial step. Real understanding of the business problem.
It's more than just the numbers. It's about translating those numbers into a tangible, real-world impact.
Okay, so we've talked about how important the metric is. But what if, say, I need more than one machine learning model, plus pre-processing steps?
Then, we need pipelines. They chain everything together, and that's where it gets complicated but also powerful. They handle all the pre-processing, feature engineering, and the model itself.
And how does the pipeline interact with evaluation?
That's where grid search CV and cross-validation become crucial again. They allow us to evaluate how well the entire pipeline performs.
Okay, so it's like a comprehensive approach to building an optimal model, but also measuring its real-world impact?
Exactly. You see how all this fits together?
Totally. So, this whole discussion highlights the importance of the evaluation metric tailored to the specific business problem.
Exactly. We're taking a look at the whole picture, not just the numbers.
And the cost of incorrect predictions so important.
Correct. This way you get a more practical, holistic picture.
And you've brought up some really crucial issues, Sarah.
It's about going beyond the algorithm and understanding its impact. How do we integrate this better into practice?
A truly important takeaway. What's the last piece of the puzzle?
The last piece is recognizing that the evaluation isn't just about selecting the best model. It's about understanding its real-world applications. We must understand the implications of our predictions on the business side.
And this is fundamental for real-world applications.
Precisely.
Well, Sarah, that was a fascinating journey through evaluation metrics and business decisions. Thank you.
You're welcome, Jane. It's been a pleasure discussing this.
Listeners, this was a critical conversation about using machine learning tools effectively. Don't just build a model. Understand why you're building it and what it will mean in the real world. Subscribe to the Data Deep Dive for more insights like this, delving into the practical, business-relevant applications of machine learning.
Definitely. Subscribe and be part of this data-driven journey.
Thank you all and goodbye.
Goodbye.